There it is.
It's just like, it's a very, I hate it that like this is fit, like it gets really messy because it's like really like small space. So like I have to make it like, it's very different.
Gotta put it on the website. Okay, so we're going to continue our tackling of the beast, which I call chapter 4. So are we ready? Okay. We're ready, right? Are you ready? Do I have to go big drama party on you? Are you ready? Are you ready? Let's get it on. Okay. So we're still in chapter 4. We're going to be in chapter 4 today and probably through tomorrow. We talked about stoichiometry. During problem solving, we'll go back and we will do another set of stoichiometry linear reactive problems. I think we can all use more practice on that. We went through molarity, concentrations. We talked about solubility. We started doing precipitation reactions, a review of that. So that's one of the 3 main types of chemistry discussed in chapter 4. We'll get through acid-base today. Maybe we'll start redox. We'll see. Okay. So I wanted to kind of review, or not review, but start off doing a stoichiometry problem with a precipitation reaction. So the overall pattern of this is you discuss the chemistry. You got precipitation, acid-base, or redox chemistry. And then from each kind of chemistry, you do stoichiometry. That's sort of the overall picture. So we've talked about precipitation chemistry. Some of you may remember it as being called double replacement chemistry, or double displacement. But why wouldn't double displacement be as specific as calling it precipitation? And the reason why is because acid-base chemistry is also double displacement, right? So when you say, if you look at a reaction and you call it a double displacement reaction, it's not really calling it specific enough for my liking, because acid-base and precipitation are both double displacement reactions. It's just that, but they're still different. So we'll get to acid-base momentarily, but for now we'll do a precipitation example, and it uses molarity instead of just grams. Okay, so this question asks, how many grams of precipitate forms when 2.64 liters of 1.2 molar sodium phosphate is reacted with excess calcium chloride? Okay, so the hardest thing to do with all of these, first and foremost, is nomenclature and then writing the chemistry out from that. Okay, so any idea where we might want to start? Yeah, write the chemical reaction. But in order to do the chemical reaction, we have to do nomenclature, right? We have to get the nomenclature, then write the chemical reaction from that, and then we can go about worrying about doing the math. Okay, so what would be the chemistry here? So what's the formula for sodium phosphate? All right, so phosphates, PO4 3 minus. We know we need 3 sodium pluses then to match that up. So we got sodium phosphate. Formula for calcium chloride is what? CaCl2. Okay, and then the products are going to be what? Right, so you're going to take the anion of the phosphate and combine it with calcium. Okay, so what is the formula for calcium phosphate? So calcium is always 2 plus. Phosphate is always 3 minus. Okay, so the 3 comes down, becomes the subscript for the calcium, and then the 2 plus, the 2 comes down, becomes the subscript for the phosphate. Right? So here's my formula for calcium phosphate. And then we have sodium chloride as the other one. All right. Then we got to balance it. So balancing gives us, let's see, free sodiums. We've got only one here. So we got 3 there. We've got, now one way to balance these that's easier than just looking at individual atoms is to say, okay, I got 1 phosphate, but I've got 2 phosphates over here. I can balance groups of atoms. So actually I need to put a 2 in front of the phosphate, which means I now have to have 6 in front of the sodium. Okay, and then for the calcium, I got 3, and then the chloride is balanced, right? 6 chlorines. Okay, so that's our chemistry. Now it says, how many grams of precipitate moles? How do I know what the precipitate is? Right, so remembering your solubility rules, sodium chloride is always aqueous because all sodium salts are always soluble. So that's aqueous, but the calcium phosphate is going to be solvent because it's phosphate salts are usually insoluble. Okay, so there's our balanced chemical reaction with phases. If you can do that, you've got probably, I don't know, at least 50% of the battle taken care of. That's probably the hardest part, is just nomenclature, writing the chemistry. You'll find this out, if you don't know already, when we do practice problems upstairs. The problems are going to give you this kind of verbiage. They're going to give you the written out name, and they're going to expect you to write the chemistry out from the verbiage. And you're going to struggle with it for a while, but once you get your nomenclature down, then it'll be easier. Okay, so we have our balanced reaction. What do we do then? Right, so, is this a limiting reactant problem, or is this a more simple Megan-Trainor-like problem? How many do you say Megan-Trainor? How many do you say limiting reactant? How many of you are unsure? How many of you are still asleep today? Okay, so we have just 2 numbers given there. We have a liters and a molarity. Okay, and it's a liters and a molarity of sodium phosphate only, right? And it says excess calcium chloride. So if you have a reactant that is in excess and there's only one other reactant, that means that you can just assume that the sodium phosphate in this case is the limiting reactant. You don't have to go through the balance table and the gyrations of having to do all that. Okay, so if the other one's in excess, then you know what's going to run out is the sodium phosphate, and as a result of that, you can just work off of that, and it's a simple Megan-Trainor kind of problem. So instead of grams, moles, grams, it's going to be molarity, moles, grams. Okay, that's the only difference with this problem relative to what you've seen before. Okay, so how do we get from molarity to moles, grams? Okay, so we know that since molarity is equal to moles of solute per liter solution, we know then that if we're going to get the moles from that, we have to say, okay, moles are equal to molarity times volume. Okay, or you could say volume times molarity. Okay, so just multiply volume over, you get that. And so we're going to do that for this. So the volume here is 2.64 liters. So we have 2.64 liters times the molarity. Okay, and the molarity is 1.2 molar. What does 1.2 molar mean in terms of the units? Like, what are the real units of that? Moles per liter, right? So if we say moles of sodium phosphate per 1 liter of solution, so the liters of solution will then cancel. And then going from there, this is just like what we've done before. right? So what's the next thing we have to do? It's still multiple grams are still, yeah, mole ratio, stoichiometric mole ratio, right? Not just any mole ratio, it's the stoichiometric. So what is the stoichiometric mole ratio? What is it asking me for? How many grams to precipitate, right? So what mole ratio do I use?
For 2 moles of sodium phosphate, you get 1 mole of calcium phosphate.
Right, so I've got 1 of the calcium phosphate precipitate for every 2 of my limiting reactant. Okay, or my 1 reactant that gives me information about. What if it didn't say excess there? Could you still pinpoint this as not being limiting reactant? And the answer is yes, because it only gives you 1 thing, that's what you work off of, right? So just by default. So I produced 1 mole of calcium phosphate for every 2 moles of the sodium phosphate I consume. And then lastly, just to continue this down here, there's one last conversion I gotta use. And molar mass, right? So calcium phosphate has the molar mass, just to save some time here, 310.18 grams of calcium phosphate per 1 mole of the calcium phosphate. Notice how I'm taking the painstaking detail of writing out the identifier, not just the unit, right? Because otherwise you're not going to, maybe necessarily realize you're canceling the right compound. Okay, so running this would give us 491.3. How many sig figs should I round that to?
2.
Yeah, 1.2 molar is just 2 sig figs, right? So what do I round it to?
4.
So if the 9 is the last sig fig, then it just becomes what? 490, right? So it's just going to be 490. Yeah.
If you put 5.0 times 10 to the second, would that be right?
If you put 5.0 times 10 to the second, that would be incorrect. So if you round it up to 5 here, it means you're rounding the 9 up into the 4. That means you're just rounding to 1 sig fig at that point. Although 5.0 has 2 sig figs in it, but what you're doing is you're rounding it to 1 and then you're changing it back versus just taking the number as is, right? Because 491 is a lot closer to 490 than it is to 500. You know what I mean? All right. All right. Yeah.
How would the question be worded if you did want to do a limiting reactant?
Right, so what if it was a limiting reactant? So at that point, the question would read something like the same as what you have here for sodium phosphate, but then it would say something like, is reacted with so many liters of a molar solution of the calcium chloride. They'd have to give you another volume and molarity for the other reactant. And then at that point, you have to go through the limiting reactant process of an amount stable and all that stuff. We'll do a couple like that probably next week. Okay, we'll practice that problem solving. Okay, anything else? All right. So this is an example of a simple stoichiometry problem with precipitation chemistry.